So I'm going to begin with some heavy-duty domain theory. Down at the bottom you've got the considered relation, which goes way back, like M plus K patterns. But more recently, we've got more sophisticated, better than relationship. And so Phil, for example, has a paper that listlessness is better than laziness. And one of the most interesting ones was planner, which was then inferior to conniver, which was then inferior to scheme. And then Phil has a paper calculating is better than scheming. So I thought I would add in pointlessness, which must be even better than listlessness. So Phil asked the question in one of his papers, or many of them, shall I be pure? And I'm going to talk about data structures, and in particular, pure functional arrays, or perhaps a better name is persistent arrays. And what I mean by the data structure is this API. So we have a constant empty, which is an array with no elements, and empty always exists. And we have a lookup function, so you can look up in an array A at an index I, and you may or may not get back an element at that index. And update is the most interesting one. You can update an array A with an index I and a value, and you'll get back a new array. And the important point about this is that update does not change the array A. It gives you a new array. And the new array is just like the old array, except it has this new element. But you can go back and use the previous array if you like. And it's very easy to specify the semantics of these. If you look up in the empty array, you get nothing. And if you look up an array created by an update at an index, if the index matches the index that you updated, you get that element. And otherwise it will recursively try the array that was built on. Now, there are some additional operations in the API. In particular, you can make the data structure extensible and sparse, and it can do some associative searching. So I call this ESF arrays because of some of these other operations. But actually, I'm just going to be talking about lookup and update. Now, the thing that makes them tricky to implement efficiently is sharing. So, for example, if I define a sequence of arrays by updating, and I have to start with empty, and then I update each array in turn. If you look at the earlier elements, like index 100 is mapped to 3.14, that element is actually a member of all of these arrays. So this data structure gives you a great deal of sharing. Now, in ordinary Fortran-like arrays, if you do an array lookup or an array modification, the time and space is always order 1. It's constant time. People are accustomed to that. But if you use the specification I just showed as an implementation, you can get quite slow lookups. And there are a variety of ways to implement pure functional arrays. You can trade off the inefficiency of lookup and the inefficiency of update, but you have an efficiency nonetheless. My aim is to try to get really efficient implementation, and the key observation here is that we have to maintain the sharing. We cannot duplicate the elements. So, for example, the element, the value 3.14, needs to be in the memory of the machine, only one copy of it. Otherwise, we're going to have very bad performance. And I'll make a conjecture, which is that this data structure is slow. What I mean by that is there doesn't exist an implementation of the operations that gives you order 1 access for all operations, regardless of the history of updates that you've done. And that leads me to the main result here, which is that I'm in fact going to violate that by showing you an algorithm that does exactly all that. So I'd like to explain what I mean here. So imagine a complexity theory game. So as a computer scientist, you're given some kind of a programming model like the random access machine or some equivalent model and a problem to solve, like you want to do sorting. And what you need to do is to build a valid program using the rules of the language to achieve the complexity. And so that's normal computational complexity. I'm going to change the rules of the game. And instead of being given the machine model, like the random access machine, I'm going to say you're given a lot of flip-flops and logic gates. And then you have to connect up these components to come up with a machine that solves your problem. And so this is, in a sense, a very realistic way of viewing building computing systems. Now, one approach to doing this is take all your logic gates, and of course, hardware people and software people live on different sides of the planet and they never talk to each other. So you'll get a hardware person to connect up those logic gates to implement a von Neumann architecture or a RAM machine. And then you'll get a software person to write a program for it. Now, if the conjecture I put up is true, which I believe it is, you've already lost the game. The von Neumann architecture is inherently inefficient. A second alternative approach is that you can use these logic gates and flip-flops, but connect them up in a different way that's not equivalent to the RAM model, but that lets you win the game. And that's the approach I'm going to take here. So some people call this kind of area hardware-software co-design, where you are not simply programming a given computer, but you can bring to bear hardware design techniques as well as software design techniques to solve a problem. And of course, the conjecture I put up, I didn't state the unstated assumption, which is that we're assuming a random access machine model. And by changing the rules of the game, I'm making explicit that the algorithm runs on hardware. Now, I'm not going to give the details of how the algorithm works, but I'd just like to describe a few of the highlights or the lowlights of how this works. The key idea here is kind of changing perspective, which I call pointlessness. This is not point-free, as you are familiar with, but more like pointer-free. We're not going to have tree data structures where there's an address or something like that that points at another object. One way to think about it is that a conventional array knows where its elements are. Given the address of the array, you can do some arithmetic and find out where the ith element is. I'm going to turn this around completely. So an array is going to be represented by a handle, which is just a random number, like 39, and it has no meaning. You can compare it with another array handle, but there is no useful computation you can do on it. And that array does not know what its elements are. The elements, which are bindings from an index to a value, these are placed in memory cells at just any random location. It can be anywhere in the machine. So they're just floating around randomly. And every element knows the set of arrays which contain that element. And I call that the inclusion set for the element. And the basic idea is we're going to do a sort of fancy associative search in hardware to find the relevant information without having to follow pointers. And one worry is, how can you even represent an inclusion set? Because it could be that an element belongs to as many arrays as there are words of memory in the machine. And of course, you cannot represent an arbitrary set in a fixed number of bits such that you can always check set membership in a fixed amount of time. But the inclusion sets are not random sets. They must have resulted from a sequence of update operations, and that enforces a number of invariants on the data structure. And it turns out we can just barely actually represent the inclusion sets using a pair of natural numbers. So I'll call them low and high. And the idea is that an array with a code like 50 belongs to the inclusion set of an element if low for that element is less than or equal to the array code less than or equal to high. And so the nice thing about this is it's a fixed amount of bits, and it takes a fixed amount of time to do these comparisons.
It's completely unrelated, but it's those who take 50. So it'd be hard to construct that.
Yeah, so actually the handles cannot be used for this comparison because making this comparison work requires these strong properties on what the array codes actually are. So every time you do an update, half the array codes in the machine change. And so we'll have an external handle to the array, which is an arbitrarily chosen number. That's never going to change. And then the machine has a mapping from the array handles to the current value of the code. And this mapping will change, it can change every clock cycle. Now, the system has 3 levels of implementation. There's a digital circuit, which is specified in a functional hardware description language. And then there is a set of algorithms on the circuit that implement a family of combinators. They are related to map, fold, and scan, but they're slightly special versions of map, fold, and scan. And then the implementations of update and lookup and the other operations as well are carried out using these combinators. And actually all 3 of these levels are specified functionally and have proofs or derivations behind them. So calculating is indeed better than scheming. Let's talk about the hardware just a little bit. I think an important intuition is to start with what an ordinary random access memory does. It actually has a tree of decoders, and you cannot in hardware access a word of memory in order 1 time. We normally just ignore the fact that there's a logarithmic time access. The tree of multiplexers here in memory are not doing very much work. All they're doing is decoding the address bits. And what I'm going to do is put a little bit more hardware into this tree and do a little bit more computation. And furthermore, each of the memory cells has a little bit of local computation, not much. It has the ability to compare, increment, and the like, and they can all do it in parallel. So this doesn't change the complexity of the hardware in either time or number of components. It does increase it by a constant factor, but we can do more with this. And I'm not going to go through the details, but here's the type of what this circuit does during a clock cycle, and a little bit of the description of the circuit. And the combinators can be derived. You don't have to write them out as programs and then prove them correct. You can state a conjecture that says basically that there exists a program which, given any valid input, computes the result that you're trying to calculate on the machine. And there's a number of slides of equational reasoning, which I'll skip over, and we end up with the solution, which is depicted here. And here is the final result. So if you're going to do T-scan-R is one of these combinators, and if you're going to do T-scan-R F, A, it can be done by a sweep in 1 clock cycle, and the leaf and node functions are defined as well. So the blue stuff there was derived. And here's a more conventional hardware-like diagram. One thing I'd like to point out in there are a number of papers on parallel scan that have incorrect results in them. And one of the reasons for this is that people generally work with a picture like this, and then work through an example of the scan taking place. And a side condition here is that the function f needs to be associative, but it does not need to be commutative. And in some papers, they had examples using addition, which is commutative as well as associative, and they got the arguments reversed, and so they actually have an incorrect implementation of scan. So there's a nice example of why calculating is better than scheming. Just say a little bit about how the update and the other algorithms work using these. So here's a sketch of what update does, and I do not want to explain exactly what's going on here. The important point is to notice that it's all local computation. Every memory cell in the entire machine does this computation in parallel with all the other ones. And the computations taking place are comparisons of natural numbers, incrementing, and not much else. So that can all be done in constant time. Now, the algorithms are actually kind of tricky, and they need and they have a correctness proof. And the correctness proof is also carried out with equational reasoning. So this actually goes on for several pages. The ... is actually fairly long. And there are a number of cases to consider. So the proof is not as short as it looks here, but it is a pure calculation of style. One thing you can see here, x in this case happens to be an element that already exists in the array that we're updating. And that element has an inclusion set in the initial state. And so this is its inclusion set in the initial state. But its inclusion set in the new state, which happens after the update, also contains the new array that we've just created. And that's what we want. And here's just a diagram. So if anybody is interested, I have a number of examples that look sort of like this. The arrows there are not pointers. This is pointless. There is no pointer anywhere. But there are relationships among the cells that a human needs to know about to understand what's going on. But all the information that the implementation uses is just the values of all these numbers. And after performing an update, I've put into red the values of the fields that have changed. And you see that about half of them have changed and about half of them have not changed. And here's the new element that went in. And notice that there's no loss of sharing. Okay, so this is the low and high for the inclusion set. This is the rank, which is the distance from the cell up to the top of this notional tree. This is the index of the value. This is the array handle. This is actually not in the representation, but it's just a little annotation to make the example easier to follow. If you're doing a lookup, the parallel map allows all the cells in parallel to compare their low and high with the code of the array that you're looking up. And so in one clock cycle, they all turn on, and then we have to compare with the index to see which one we want. Now, actually, I've always conceived of this as an algorithm meant to run on a VLSI circuit. We started thinking about simulating it. So there's actually, the whole thing is specified in a combination of the functional hardware description language and Haskell. The functional hardware description language is also Haskell. And so I can run simulations of it. But wouldn't it be nice to run the simulation on a parallel computer? So we did some experiments with using a GPU. And one of the things that comes out of this is GPUs are very, very slow compared to a circuit. But on the other hand, they can do some things that a single port in memory cannot do. And one of the things that GPU can do is copy an array from one place to another place. And so we looked at doing some operations like bulk update. So instead of just updating an array with one value, why don't we try taking an array of values, 1,000 values that are in ordinary RAM, and updating the array with all of those with a sequence of consecutive indexes. Anyway, we've implemented bulk update and bulk lookup and parallelism. And I'd like to say a little bit about the GPU implementation. So the thing to focus on in terms of computer hardware is the granularity. And the conception of ESF arrays is that every memory cell has a little bit of local computation, so it is extremely fine-grained. The GPU is much coarser-grained. And here's a way to, I like to think of it. So a CPU has typically 10 to the 7 transistors in it, and the memory for it is several orders of magnitude larger, maybe 10 to the 10. So big memory, big CPU. A multi-core is just more of the same. If you go to a GPU, the GPU we used had 32 processors and 512 CUDA cores. So it's quite a bit more parallel than a typical multi-core, but still big processors and not very many of them. On an FPGA, we could do better, but the way I like to think of these algorithms is that the processing and the memory have dissolved. And so a processor might have on the order of 1,000 bits of memory and 1,000 transistors in it. And think about really large numbers of processors. So anyway, this is yeah. Oh yeah. That's right. Yeah, power consumption is a big issue. So in particular, you would not want to use this for modeling ordinary data structures. It would be counterproductive unless you're actually using the sharing and the capabilities that this data structure has. So yes, it's going to be higher power consumption. Absolutely. Yeah, that's right. Yeah. I don't know exactly. Around let me defer that because I don't know exactly. So we've implemented this on a GPU using CUDA. I'd like to tell you something about CUDA for those of you who would like to prove programs correct. There are people who try to prove correctness of CUDA programs. Now, the code we've got, so it's lots of C code, and there's this thing. If 2 plus 2 equals 5, then print 2 is getting bigger. And then we go on to more C code. Now, if you take out that red code, the program does not work. Furthermore, CUDA is sensitive to what's inside comments. And so anybody who is doing formal methods improving properties of CUDA programs needs to take on board stuff like this. And if they ever improve the optimizer and remove this as dead code, I assume that the program will quit working, which is a little bit worrying. Here's some times on the bulk update. For example, if you're doing a bulk update with 256 values, or you're doing one update and putting in 256 values into the data structure, the CPP, this is a library from C++, which has the same, a similar API to ESF arrays, but it will get incorrect results. It's the responsibility of the programmer to make sure that you're handling sharing correctly. So it's not actually a correct full implementation. But we tried using it in a context where it is getting correct results. And it's interesting to see that it starts out quite a bit faster than the GPU, but the GPU's performance scales up reasonably well. And search is even more dramatic. And I don't have the figures for ordinary update and lookup. On those, the GPU time is just constant. It's the 11 microseconds, I forget what it is. It's just that way all the way until the end of the table. Another Phil's old papers from a long time ago. He used to get his hands dirty. He had a paper on fixing some space leaks with a garbage collector. And there's actually an interesting garbage collector for this system. The algorithm is here, and I'll just tell you the main property of it. When you delete an array, that's a promise that you're not going to update it or look it up in the future. And the array gets deleted in constant time. And the system has the property that it deletes all of the stuff that is deletable, and it keeps all the stuff that might be needed in the future. But there is a space leak, which I'm currently working on using associative techniques. In this picture, if you delete an array, for example, if I delete this array, we can't actually reclaim any of the storage because it's shared with that one. But it does change the representation of the system, and later on, if we then delete this, both of those get reclaimed. So delete may not reclaim any storage at all, or it may reclaim a lot all in one fell swoop, but it always gets the right amount. So the bottom line here is this data structure, if it's running on VLSI hardware, it does actually have the same time and space complexity as ordinary Fortran arrays. So I'll stop there.